So let us assume that we have angle action variables, theta and j. And let's assume that these actions are integrals of motion. Because j's are constants of motion, then j dot have to be zero. Therefore, the Hamiltonian must be independent of the coordinates theta. That is, h is only a function of the actions. Consequently, then, the other Hamiltonian equation, the one for the coordinate theta dot, is equal to the derivative of the Hamiltonian with respect to j. So this must be a function of j alone. Let's call this derivative omega, and these are functions of j. Now j is a constant of motion, therefore this is constant. So we already have then the full solution for the angle. The angles, they increase linearly with time if these omegas are non-zero. Thus, if we can find the three integrals of motion as the actions of a system of canonical coordinates, we completely solve the system. So let's restrict our attention then to bound orbits. Let's have an elliptical orbit. So in this case then, the Cartesian coordinates, x and y, they cannot increase without limit as the angles do. So from that, we infer that the Cartesian coordinates x must be periodic functions of theta. So we can scale theta so that x returns to its original value after theta has increased by 2 pi. We can expand them, we can write the Cartesian coordinates in terms of Fourier expansions, in terms of a Fourier series, where the sum is over all of the wave vectors n, and we can eliminate theta using this equation that we have already found. So in a way, what you have here is an expression that looks like an expansion in polar coordinates, where you would have coefficients that depend on radius and oscillations in the angle. And indeed, this is an apt analogy. If you think of phase space, Q and P, then the angle theta is just like the angle theta in polar coordinates. And these different radii would be the values of the different actions, J1, J2, J3. So you can convert Q and P into theta and J in pretty much the same way that you would convert Cartesian coordinates into polar coordinates. So that states that there must be also transformations between the canonical coordinates QP and the canonical coordinates theta j. One of these is the Poincaré invariant.